This is a presentation on Capsim buffer management. In general, what we want to describe is how connections work in Capsim when you connect blocks and you create complex simulations with multi-rate single processing feedback, and in some cases where you have both synchronous data flow and asynchronous data flow. For example, when you do a combination of MAC layer and physical layer simulations in Capsim. This will be a very short description, but hopefully we'll get the ideas across so that you can see how Capsim is quite capable in modeling and simulating almost any communication system or digital signal processing system that you may encounter. Also, with this presentation, you'll get a good idea about how to set up your simulation in case you run into problems and issues. The original model for Capsim is Blossom, which was developed by David Messerschmidt at University of California at Berkeley, and was described in this paper in 1984, a tool for structured functional simulation. This is a very powerful simulation model in which blocks are connected through first-in, first-out buffers, and it is very flexible, as we will describe. Also, this paper is very important, Structured Interconnection of Simulation Programs. Both of these papers are available in PDF format from the SourceForge website for Capsim text mode kernel at this address shown here. If you want to dive in some more into the model behind Capsim, these are good papers to review. We should also point out that Capsim itself is an extension and quite a bit of enhancements to Blossom, and Capsim has been in development since 1987 and includes many enhancements in terms of both memory management, plugging of many memory leaks, and of course enhancements to the efficiency of the simulation. In this diagram, we show a simple topology in which we have a sinusoidal generator over here, we have an adder, and another source block called Gauss, which generates samples with a Gaussian normal distribution. And over here we have a block that plots the samples. Now in a Capsim simulation, what happens is that the simulation kernel schedules these blocks for execution, and it also has a special consideration for source blocks like the sine wave generator here and the Gauss wave generator over here. Now during execution, typically when you design a source block, when the scheduler visits the source block will generate a number of samples. For example, the sinusoid can generate, for example, 1 million samples, but it doesn't generate all 1 million samples at one time. What it does is it generates, for example, 128 samples at a time. These samples are then processed by the blocks, and the results are, for example, in this case, displayed or plotted. Next time around, the sine wave is scheduled again. It'll generate another 128 samples, and so forth until it exhausts all 1 million samples, and then it would stop generating samples. The kernel determines that a simulation has completed based on a deadlock condition. And a deadlock occurs when blocks have no samples either to input or to output, and there's no activity on the block's input and output buffers. And this holds true for all blocks within the system, and in that case the kernel determines that we have deadlock and the simulation terminates. We'll get into more of that later. So in this simple case, as we mentioned, the sine wave will generate 128 samples, and the Gauss block would also generate 128 samples. The adder block would check the minimum number of samples available on its buffers. In this case, there'll be 128, and it will process all 128 samples, outputting the sum on its output buffer. And the plot block will look at its input buffer and see that there are 128 samples available there. It would collect those samples and plot them. One thing we need to point out is that the plot star, for example, will plot as many samples as it can collect. For example, if the sine wave is going to generate 1 million samples, and the Gaussian block is also going to generate 1 million samples, and the plot will collect all the samples, and when the simulation terminates, it would actually collect all million samples and plot those results. So in this situation, we don't have any issues, and the simulation is very efficient. Each buffer shown over here is actually a first-in, first-out buffer. And for example, the sine wave actually outputs samples onto this first-in, first-out buffer. When the first-in, first-out buffer is created, it is created with, for example, 128 cells. Each cell will contain a floating point sample in this case. And if for one reason or the other the sine wave wants to generate more samples and the buffer is full, then another 128 more cells are added to the first in first out buffer. We'll describe those later. But in general, what happens is that the 128 samples that the sine wave generates matches the 128 samples or cells which the FIFO is created with, and the add block would consume all those samples and the buffers never overflow in this case, and you have a nice smooth simulation, in which case the add block basically receives 128 samples, adds all the 128 samples to each other and outputs them to the output buffer, and the plot block basically collects those samples in order to eventually plot all million samples, for example. So let's review this again. The Capsim kernel will schedule the blocks for execution in a particular order. The sine wave and the Gauss block are source blocks. Each time they are visited, they will output a chunk of data, in this case 128 samples. The 128 samples are processed by the add block and output to the plot block. The plot block would also input all 128 samples and collect them to eventually plot all 1 million samples. One of the nice things about a Capsim simulation is that there is a very nice bounded size on the memory required in order to do a simulation. In this case, it's limited to 128 cells here, 128 cells on this buffer, and 128 cells on this buffer. Even though we can generate 10 million, 100 million samples, the actual memory used in Capsim is limited. This is a very important feature of Capsim. So you can actually simulate an unlimited number of samples, yet the memory footprint doesn't grow. This is especially important in doing bit error rate simulations, where you might generate, for example, 1 billion bits in order to determine the bit error rate in a fiber optic communication link, for example. So this is a case where we don't have much issue. The footprint is bounded, and we don't have multi-rate single processing or feedback, and those are the topics we'll get into in the next section. During each simulation, Capsim produces a file called buffer.dat with a lowercase b, and you can always examine this file in order to see what's happening with the buffers in a Capsim topology during simulations. In this case, we had 3 blocks: the sine wave generator, the Gauss generator, and also the add block and the plot block. And this shows that the sine wave generator actually created one allocation of 128 cells on its output buffer. Similarly, the Gauss block, which is also a source generated, created one segment or 128 cells or 128 samples on its output buffer, and the same is true for the add block. Here we show the legend for reading off the data in the buffer.dat. Here we show the sine wave. Sine 0 is the name of the block. The port number or buffer number is shown here. And this number here is the number of segments that were created on its buffer associated with port 0. Each segment is by default 128 cells. And by the way, this can be adjusted in Capsim in order to optimize the simulation. In this case, each cell is a floating point sample. In general, in Capsim, cells can be, for example, full images, full matrices, or complex numbers, or whatever you so desire. So in this case, even though we're generating, for example, 1 million samples, the buffers are bounded and are only the size of 128 cells, shown here, one segment for each. We don't have a problem. Here's a result of a simulation of the previous block diagram with 128 samples, where we have the sine wave plus additive Gaussian noise. And here we have the simulation with 10 million samples. And just to note that the footprint for the simulation did not increase at all. It's the same footprint that was used for 128 samples. So it doesn't matter whether we simulate 10 million samples, 100 million samples, 1 billion samples, or just 128 samples. The memory footprint does not grow in Capsim. In this block diagram, we show a situation where we have multi-rate single processing. For example, in a digital communication link, the data block here generates binary data. This is the B data block. So it will generate, for example, 128 samples per visit. It can generate a gigabits, for example, but every visit it'll only generate 128 bits and put those samples or bits on its output buffer. The coder block, however, maps the bits to symbols and also increases the rate, in this case by a factor of 8. So for every input sample, it'll generate 8 output samples. In this case, an impulse for the symbol and 7 zeros. These are input to the pulse shaping filter here, and Nyquist, a square root Nyquist pulse shaping filter for the transmit side that will filter the samples. It goes to the add block. In this case, it is only passing the data through since we're not connecting any noise source yet. At the receiver, we have a square root Nyquist filter, and we look at the eye diagram over here. So this is a case where we have multi-rate signal processing. For every input bit, we generate 8 output samples for the coder, which are actually impulses that are impulses into the square root Nyquist filter. We have the impulse responses superposition over here. And overall, we have a Nyquist pulse shaping, and we'll look at the eye diagram. Here's the result of the simulation. This is the actual time domain, and here is the actual eye diagram, and we're using 128 bits in this case. Now the next step is to actually look at the file buffer.dat and see how the buffers grow, in this case where we have multi-rate signal processing. If we look at buffer.dat, again, notice the legend where we have the block name, the port number, and the number of segments that were allocated. For the bdata block, which generates the binary data, only one segment is allocated because it'll generate 128 bits that will be used in the buffer, which is also allocated with 128 cells, and we don't have any problem here. Line code, however, will generate multiple segments, and the reason for this is that line code will consume all 128 bits that were generated by bdata and output for those 128 bits 8 times that many samples. And since each segment is only 128 samples, it would actually have to allocate 8 segments in order to accommodate all the samples or bits generated by bdata. So we see that line code would actually use 8 segments in order to accommodate the oversampling bits, because it'll generate more samples per bit. Also, the square root Nyquist filter allocates 8 segments for its output, and so does the add block, and so does the square root Nyquist filter at the receiver. So in the case of multi-rate signal processing, we see that the memory footprint will actually increase to accommodate the multi-rate signal processing. Now this is not an issue, especially the case that even though we generate, for example, a gigabits, the footprint doesn't increase and will remain as shown over here, regardless of how many bits are generated. We should note that since these buffers, let's go back to the diagram, the actual topology, we should note that these simulations are very efficient because for every bit that's generated, we're generating 8 samples due to oversampling or multi-rate signal processing. However, each block, for example, that processes these samples, once it is visited by the kernel in order to do its execution, it will consume all the samples on its input buffer and very efficiently process all those samples and output them on its output buffer. So the simulation is very efficient. You have one call to this block, and this block will consume all its input samples and output them before returning back to the kernel, so it's very efficient. And as we said, we have a bounded memory footprint, even though you can simulate, for example, a gigabit worth of information. Typically in a digital communication link, we would actually have a decimator out here, which would actually reduce the sampling rate, that would actually reduce the sampling rate and so forth. So you can have multiple blocks which actually increase or decrease the sampling rate in a simulation. We'll see some of that later. So to summarize, when you have multi-rate signal processing, you do have situations where the size of the buffer will grow in order to accommodate the multi-rate signal processing. And later on down the pipeline, when you actually decrease the sampling rate, of course the buffer sizes will decrease. But it's important to note that during multi-rate signal processing, the footprint does not increase even though you might generate gigabits worth of data. Another very important aspect of the way Capsim does simulations is the fact that multi-rate signal processing is done at the natural rate for each block. So this block, this Nyquist filter block, for example, square root Nyquist filter block here, runs at its natural rate, whereas the binary data generator runs at its natural rate, which is at the baseband, the bit rate, and the filter runs at its rate, which is at 8 times the bit rate. So each block runs at its natural sampling rate. This is very different than some of the other simulation models and the way they accommodate multi-rate single processing, which they had quite a bit of problems, in fact, and inefficiencies. But Capsim actually has the added advantage that each block runs at its natural sampling rate. You don't have a central sampling rate or clock per se, but each block runs at its natural sampling rate. This is very efficient and provides for very efficient and flexible simulations. Now let's consider the case where we actually add the block Gauss, which generates normal Gaussian samples, normally distributed Gaussian samples, and it's connected to the add block, and we're trying to model a channel with additive white Gaussian noise. Now here we get an interesting situation. The binary data generates 128 bits. The coder then upsamples that by a factor of 8. So for every bit here, we get 128 samples here. And as we mentioned before, the buffer here actually grows because by default each buffer is set to 128 cells. And since this coder block wants to process all 128 bits on its input port, it would actually generate 8 times that number of samples. So for example, for every bit it'll generate 128 samples. That would consume all the allocated segments for that buffer, so the buffer will actually grow for the next input bit. And as we showed, it'll actually grow to 8 segments, which are each 128 cells, in order to accommodate the multi-rate. Now that's not an issue. In fact, it's very efficient because the filtering block here would actually consume all those samples on its call and efficiently process all those samples and output it on its buffer. Now the buffers would grow because in general, in order to limit the memory footprint, we limit buffer sizes to, for example, 128 segments, and they will only grow if they need to. We don't actually go and allocate, for example, 8 times 128 for each buffer. We actually limit it to 128 samples, but they will grow in order to accommodate multi-rate single processing. Now here's a very important situation that arises. If we look at the block here, it will generate 128 samples, and the data block generates 128 samples when it is visited. These are source blocks. So when we look at the add block here, on the one hand, on this connection here, it sees 8 times 128 samples, but over here, on the first visit to the Gauss block, it'll only generate 128 samples. So the add block will actually consume only 128 samples because it will consume the 128 samples from the Gauss block and the 128 samples here, and output that to the output filtering block. Now what happens is the Gauss block, if it's set to 128 samples, then it would then stop the simulation, and we've only processed 128 samples. So in order to actually simulate this correctly, we need to set the parameters in the Gauss block to generate 8 times 128 samples, because that's how many samples we're actually going to need to process. So the add block has to actually process 8 times 128 samples. So what we do is we set the Gauss block parameter to 8 times 128 samples. So we need to know during multi-rate single processing that the Gaussian block has to generate 8 times 128 samples in order to accommodate the 128 bits over here. So that's all nice and fine, and the simulation will actually proceed, and everything's okay. Problem occurs though when the binary data generates more than 128 samples. Let's take a look at this case. The binary data generates 1024 samples. In this case, when the kernel schedules all the blocks, it'll run through, and the binary data would generate 128 samples. It'll get upsampled, and here we have 8 times 128 samples at the input to the add block. But when the kernel visits the Gauss block, it'll only generate 128 samples. So the add block will consume all 128 samples here. It will consume 128 samples here, but we're left with 7 times 128 samples stranded on this buffer, because the add block can only process the minimum number of samples available on all its input ports. So it looks at the input port 0, input port 1. It only sees 128 samples generated by the Gauss block, although over here it has 7 times 128 due to the upsampling. So it would actually remove 128 samples and send that down the pipeline. We're stranded with 7 times 128 samples. Then what happens is the kernel visits the data block, the binary data generator again, and it'll generate again 128 samples. And it gets upsampled by a factor of 8. The Gauss block generates another 128 samples. The add block consumes 128 samples because that's all it sees on the minimum available is what it sees on the Gauss block. Even though on this block there are a number of samples, it can only process the 128 blocks. So again, we get a pileup of samples on this buffer because the add block only consumed 128 of them. Now again, when the kernel schedules the binary data block to generate again, it'll generate 128 more samples. Remember that it needs to generate 1024 samples, so it'll continue to keep generating 128 chunks of data. These get upsampled and get put on this buffer here, but the add block would only consume 128 samples at a time because the Gauss block is only generating 128 samples. So we see that in this situation we have a major problem where the buffer here is going to grow because the data is stranded and keeps piling up. Now as long as we have enough memory in the system, this is not an issue, and eventually the add block will process all the data generated, for example, for the 1024 bits, and the simulation would complete. But let's take a look at the growth of the buffer in this case. Here we show the results of buffer.dat for this situation. We see that the binary data keeps generating data, and it's all nice and fine. It only uses 128 samples, so the buffer is only one segment. Line code also generates, for example, upsamples by a factor of 8, and we see that its buffer grows. However, the Nyquist filter keeps growing because the add block only takes off 128 samples because the Gauss block is only generating 128 samples at a time. So we see that the buffer on the square root Nyquist filter grows, in this case up to 57 segments. Now eventually the simulation completes, but if the binary data keeps generating data, for example more than 1024 bits, then eventually we're going to have a buffer overflow and the simulation will just quit because it runs out of memory. So this is a problem. We need to be aware of in the way simulations are done in Capsim. And we have a very straightforward solution for this problem, and we'll get into that next. But if you consider a multi-rate single processing system and you have multiple sources, you're going to have a problem because in the Capsim simulation model, each source only generates a chunk of data at a time. It doesn't output all of its samples at one shot. It only samples chunks of data at a time, and this is very good for general simulations because it keeps the memory footprint bounded. But in this case, because of multi-rate single processing, we'll have what you call a buffer overflow on the output of the square root Nyquist filter here, because the add block doesn't consume all its samples. It only consumes the minimum available number of samples between the buffers, which is limited by the Gauss block, which only generates 128 samples. So in the next section, we'll actually get into a nice, straightforward solution to this problem. Okay, so let's take a look at a nice, straightforward solution to the buffer overflow problem in Capsim, which, as we indicate, is based on Blossom. So with the extreme flexibility and efficiency you get with a FIFO-based buffer in terms of modeling and simulating complex communication systems that we'll show later, the drawback is this issue with buffer overflow when you have multiple sources and you have multi-rate single processing. But as we'll show over here, that is not a problem at all. and you can get very efficient multi-rate signal processing with a simple trick. And this is not actually a trick, it's a better way to do a simulation in general. So instead of having the Gauss block sitting here as a source block by itself, what we do is we add a node block here, which basically takes its input samples and outputs them exactly on its output buffers. But we connect one of those buffers to the input to the Gauss block, and we pace it, so to speak. In the case of pacing, what the Gauss block does is it does not generate samples unless it has samples available on its input buffer. So a source block actually is a source block, but it also has an input port, and it generates samples only when there are samples available on its input port. So in this case, the Gauss block would generate 128 samples when it has a sample on its input port. Now what does this do? When we look at the add block, here for example, if we have 8 times 128 bits worth of samples over here, due to the multi-rate signal processing, the coder actually increasing the sampling rate, the Gauss block would not just generate 128 samples, but would generate the same number of samples that are available or generated by the upsampling. So the add block then will exhaust all of the samples on its input buffers and output the samples to its output buffer, and we don't get a case where the samples keep piling on this buffer here because the Gauss block only generates a limited number of samples instead of what it needs to generate to match the increase in sampling rate. The way we do this in Capsim is we actually design source blocks to have what you call a pacer at the input. Actually, the data block also has that pacer, but if it's not connected, it ignores it. The Gauss block, if in fact an input buffer is connected, then it would pace itself to that input buffer, and instead of indicating to the Gauss block how many samples to generate, because we really don't know, that's governed by the block, the B data block here. That's where we want to tell it how many bits to generate in a digital communication link. The Gauss block, actually we set the number of samples equal to -1. In this case, the Gauss block ignores the parameter. It doesn't care how many samples it needs to generate. It paces the number of samples it needs to generate based on its input buffer. It's very important to note that the Gauss buffer doesn't care what the sample values are here. It just uses that to pace itself, and it generates a normal Gaussian distribution, in our case white Gaussian noise, in order to model the channel. So let's take a look at the buffer growth in this case. By the way, here is the simulation results. We're seeing that we're generating 9,000 samples in this case, and we have the eye diagram with the additive white Gaussian noise. And let's take a look at the buffer.dat data and see the buffer growth. The buffers, as you can see, are totally bounded, that we don't have buffer overflow and the problem is solved. This is the results of buffer.dat when we did not add pacing, and we saw that the buffer actually grew to 57 segments because of the pileup, in the case where the add block only processed 128 samples at a time. So compare this situation to this situation, and we see that the buffer on the square root Nyquist filter is bounded, and we've solved the problem. In general, in these kind of situations, where we actually add pacing, a very straightforward, simple solution, which makes a lot of sense in doing a simulation, then we have cases where we can simulate digital communication links with gigabits of data, and the memory footprint is bounded and does not grow beyond a certain limit in order to accommodate the multi-rate signal process. And many times in Capsim we simulate, for example, fiber optic links in which we generate gigabits of data in order to get the bit error rate with no problem at all. In Capsim simulations with multi-rate signal processing, you can simulate billions and billions of worth of bits with no issues at all. And again, because of the fact that each block basically consumes all its input samples and runs on a per call basis, we have very efficient simulations. Okay, so the next important topic is of course feedback. In any block diagram communication system, we need to figure out, for for that particular simulation model or simulation kernel or methodology, how does it handle feedback? Here we show a simple feedback system in which we have a low-pass filter implemented discretely. We have an impulse that generates an impulse, in this case a 1 followed by 127 zeros, for example, for 128 samples. You can actually specify to generate more samples. Here we have the add block, which basically adds its input blocks. And here we show the node block, which takes its input data samples and forks them out to the output samples. And we're implementing a low-pass filter, so it takes the sample, it feeds it through a gain, in this case, for example, 0.9 or something, minus 0.9. But here's the key thing. In order to implement a low-pass filter, we need to delay by one sample and then add it back. And as we can see in the next plot, we see the actual plot of the impulse response of the low-pass filter, then it just decays out and goes to 0. The block here is a sync block, which just basically consumes its samples and doesn't do anything. The plot block is what we showed the results for. It basically gathers all the samples at its input and then plots them. The plot block is very interesting. In fact, the plot block, if you generate 1 million samples, it would just sit there and collect those samples, and at the very end of the simulation during wrap-up code, it will actually plot those results. It actually has another mode of operation in which it would plot samples on a window basis as they are generated, so you get a nice dynamic effect. But its default is to actually statically sit there and collect all its data and in wrap-up code plot the results. So here we have a situation where we have feedback, and let's discuss how Capsim handles feedback. If we look at this diagram here, we're showing that the impulse block generates 128 samples, for example. The add block looks at the sample over here and wants to process the results, so it wants to add its input ports, but at the beginning of the simulation, its input port is connected to this delay block, and the delay block is delay of one sample. Now, the delay block typically would take its input sample and delay it by one sample and output it, as shown over here. But during the initial run, beginning of the simulation, we actually don't have an output from the adder to the node block, to the gain, to the delay. So the delay doesn't have a sample at the input, so if you just leave it at that, it will not generate a sample. And the add block looks at this and it sees that it has samples over here but no sample here, so it will not generate anything. And after a while, the simulation deadlocks because there'll be a situation where none of the blocks have samples to process and they don't output samples, and that's called a deadlock, and the simulation halts. So in order to support feedback in Capsim, and this goes back to Blossom, the delay block is a special block, in which case, even though the first time it's visited, even though it has no input sample, it would output a sample. And for a delay block to operate correctly, it would actually output a 0 sample. So this is special to the delay block, and we won't get into the code for that, but it's handled very efficiently in Capsim. So the delay block, once it's visited, even though it has no samples at the input, it would actually output a sample, a 0 sample in this case. So let's take a look what happens. The impulse block generates 128 samples. The add block sees that the delay block in this case outputs a 0 sample, so now it has one sample here, it has 128 samples here, and again the add block, in order to operate correctly, looks at the minimum number of samples on its input ports and only processes the minimum number of samples. So we have one sample from the delay block, we have 128 samples here, but it'll only process one because that's the only number of the samples that the delay block outputted was only one sample. So the add block actually generates one sample. Now the sample gets input to the node block, which generates a sample, forks the sample out to its output ports, port 0 here and port 1 here, and outputs one sample, outputs another sample to the gain block outputs a sample. The delay block delays its input sample. Now notice in this case it has a sample to output, so in the next schedule for the delay block it would process the output sample And the add block again will see a sample here and process one of these samples, one more of the samples output by the impulse response. So we see that feedback actually gets kick-started. We don't have a deadlock situation, and the simulation proceeds. But there's one important point to realize, that unlike the case where we had no feedback, and let's go take a look at that. Let's take a look at the situation where we had a sine wave generator, Gaussian generator, no multi-rate single processing, no feedback. In this case, the add block basically sees 128 samples from the sinusoid generator, 128 samples from the Gaussian generator, consumes all 128 samples, outputs 128 samples to the plot block, and this is very efficient. Let's take a look at what happens when you have feedback. In the case where we have feedback, though, the add block can't consume all 128 samples from the impulse block because it only has one sample from the delay, feedback delay block. So in this feedback loop, we only process one sample at a time. So this is a concern for efficiency. So we only process one sample at a time. Even though we have 128 samples available on this port of the buffer, we only have one sample over here at a time. So this is one thing we need to realize about feedback. Now, is this a problem? It turns out to be not such a big deal because, in general, even though we're processing one sample at a time and only outputting one sample at a time, most blocks do a lot of processing when they're called to process even a single sample. So unless your simulation is built up of very primitive blocks which do simple operations, this is not, in fact, an inefficient model. In fact, it's very efficient because each block, for example, you're doing an FIR filter, you're doing a convolution, most of the time consumption is in that block doing a convolution on a per sample basis, not the fact that it gets called multiple times. So let's reflect on that. In many simulation situations, you're not building the simulation based on primitive blocks, but in fact, blocks do a lot of processing. For example, it does an FFT, or it does a convolution, and so forth. And in this case, if you process a sample at a time or multiple samples at a time, it doesn't make that big a difference, except in cases where you're building your simulation up with a lot of primitive blocks. So we've actually done some simulations. We found out that even if we insert a block here and buffer up a lot of samples so that at the rest of the pipeline they're all operating at multiple samples at a time on each call basis, there's not that much of a difference. The key point is that we're able to model feedback in Capsim simulations with the flexible buffer methodology, and in this way we can actually model very complex communication systems with feedback and digital signal processing systems with feedback and mixed analog and digital simulation systems. So we have a nice solution when you have feedback. If you have feedback, you have to insert a delay. In some cases, delay is part of the actual design. In this case, a simple IR filter. But in cases where you do have feedback, you have to insert a delay. The delay block is special in the sense that it will actually output a sample even though it has nothing on its input in the initial visit, and that kickstarts the simulation and gets you out of deadlock. So that's how you handle feedback. It's very efficient and it works like a charm. We'll see that in the next example. As an example of the very complex communication systems that can be modeled successfully and simulated in Capsim, consider the results of this paper, the joint echo cancellation equalization and timing recovery for a high-speed full duplex baseband transmission system that was presented by Jaejun Lee and myself, Ardalan, in the Milcom conference 1990. This is a very complex system. We have basically a digital subscriber line in which we have a local data generator and a remote data generator. We have echo cancellation and equalization, and we have a timing recovery loop that actually goes back and recovers the timing and resamples the input sequence while you're simultaneously doing echo cancellation and equalization. And you can see all the feedback loops in the modeling of this complex communication system, where we're actually modeling the subscriber loop and the echo through the subscriber loop, and we're adding noise, and we have channel filters and so forth. And here we're actually calculating the bit error rate. So this clearly shows that we can model successfully complex communication systems and digital signal processing systems within Capsim. This is also on the same paper where we're showing the received signal being sampled, and we actually have a timing recovery loop in which the signal is resampled again at different time phases. We go through an echo cancellor and equalizer, and we get the decisions, and this again illustrating the fact that we support timing recovery, feedback, and joint, for example, echo cancellation equalization in a Capsim simulation. The next example is also very interesting, in which we combine asynchronous and synchronous data flow. I'll be very brief here. We actually have a technical report on this, which we'll refer to you. It's on the website. Basically here we're generating binary data, and we're encoding that data in an HDLC frame using bit level protocol, and we're adding, for example, a CRC for error checking. We're sending the packet through a physical layer implemented in this case using a V29 type codec, and we're adding noise. So this is an actual model of the physical layer. It could be a whole modem in the physical layer implementation. This is actually a hierarchical block. We receive the corrupted bits. We go through the receive HDLC, which is again a bit level protocol, and we check the CRC. And if the CRC is incorrect, we have a packet error, then we do a request to send back to the data generator. So the data generator will resend the packet, and it goes through the channel again, and if it's received correctly, then we send a positive acknowledgement. Otherwise, we tell it to resend the packet, and this is an ARQ scheme, automatic repeat request scheme. So here we have a situation where, depending on the noise in the channel, we may have packets that are in error, and we have to resend them. So there is no control over the number of data that's generated during the simulation. This is very different than your synchronous data flow, where you know in advance how many samples you're going to generate and consume. In this case, the number of samples you generate depends on the noise in the channel. So here we're modeling an ARQ system with HDLC on the transmit side, HDLC on the receive side, and the data generator basically looks at a request to send in order to resend the packet in case of errors, and we also have an acknowledgement back in the case where we get correct packets. So let's take a look at the simulation result here. Here we're showing the actual packets being sent, and each time you see a peak here, that's actually a request to send due to an error. So in this case over here, we're seeing that the packet had to be sent 3 times until it went through correctly. Here we're showing the actual constellation for V.29. So here we're showing the constellation for V.29 with the noise, and this is modeling the physical layer. And again, here we're showing, like, for example, cases where we have to send a packet 3 times in order for it to get through. Here are the results of this simulation. We actually have 64 packets worth of data to send. We actually had to send 90 packets because some of those packets were in error. The bit error rate is computed and shown over here, 0.007, for example. We're showing that the total number of bits outputted was 10,906, and 20 frames were in error. So we had to actually send 20 frames that were in error. We had to resend the frames in order to get the 64 packets that we were intending on sending. So let's take a look at the case where we actually have to increase the noise. So in the next simulation results, we're seeing that since we increase the noise in the physical layer and the channel, we have to resend the packets multiple number of times in order for them to get through. Again, we try to get our 64 packets, but notice in this case, because of the increase in the noise, we actually had to send 119 packets, and we had 50 packets were in error in order to receive the 64 correct packets. In this case, the bit error rate was 0.01. So we're seeing that in the case of a ARQ system with the actual modeling of the physical layer, we have a combination of both synchronous data flow, in this case inside the physical layer, and asynchronous data flow outside the physical layer. And the actual number of samples that are generated during the simulation depends on the amount of noise and the bit error rate within the physical layer. So in Capsim, we can actually model any combination of synchronous and asynchronous data flow, and we can model complex communication systems. At this point, I'd like to discuss the simulation kernel in Capsim a little bit more. Basically, a simulation is run as follows. The kernel schedules the blocks in a particular order, and one of the particular order that it's scheduled is to find out where the source blocks are and then start from there and then lay out the blocks to be scheduled for execution following that. Actually, in Capsim, further refinements have been added, multiple levels, and some of the original Blossom kernel scheduling has been modified and changed in order to accommodate for more efficient simulations and some simulation circumstances that were anticipated later. But in general, the source block is scheduled first to be executed, followed by blocks that process the samples from the source block. Now, it is very important to understand in terms of the simulation kernel using Capsim that a source block is only run once, and then all the other blocks are ran until there is no more activity on their buffers, and then the source block is visited again and it generates samples. This is done in order to control the growth of the buffers in the Capsim simulation. So let's go over this one more time. So each source block, for example, let's take this data block here that can potentially generate a gigabit worth of data. Every time it is visited, it actually generates only, for example, 128 bits, so a chunk of bits. Those bits are then generated and go through the pipeline and are processed by the other blocks in order to generate results. And once all those samples have been consumed, the kernel then revisits the source block and generates another chunk of data. And those chunk of data are processed and consumed by the other blocks, generating results again. So in this fashion, not all of the data is generated all at once. Only chunks of data are generated, and the source block actually keeps track of how much data it has generated. Once the specified number and the parameter have been generated, then it stops generating data, and eventually the simulation runs into a deadlock where there are no more samples to be processed or consumed or generated, and the simulation stops. So this is very important to realize in the kernel simulation model and scheduling. So actually a source block is visited, generates samples, then all the other blocks are visited continuously until all the samples are consumed and a deadlock is reached, in which case the source block is again visited, it generates data, again all the data is processed. You have a case where there is no more activity on the buffer, and then the source block is visited again, another chunk of data is generated. And this also plays within the use of hierarchical blocks. So for example, hierarchical blocks are visited and all of their samples are consumed until there's no more activity within that block, and then the higher hierarchical blocks are visited and so forth. So in many cases, you can actually control the efficiency of a simulation by grouping blocks within a hierarchical block. So to summarize, Capsim provides a simulation architecture. The kernel actually schedules blocks in a particular order, and it has a lot to do with the actual topology and the hierarchical nature of the simulation. And the key point is that source blocks are only visited once. They generate a chunk of data. That chunk of data is then consumed by the other blocks, and a deadlock situation is a case in which no blocks have any more activity on their input or output buffers. In that case, the source block is revisited again, a chunk of data is generated, and the simulation continues until the source block runs out of data to generate, or there is a complete deadlock in which there is absolutely no more activity on either input or output blocks within all the blocks within a hierarchical block, and so forth. Later on, we'll have more discussions on the actual details of the simulation modeling and how the kernel arranges and schedules blocks for execution. But as we have shown, Capsim provides a very flexible simulation kernel in terms of supporting flexible first in, first out buffers to support both synchronous and asynchronous data flow and the simulation of very complex and complicated communication systems or digital signal processing systems or mixed analog and digital signal processing where you have to support, for example, multi-rate sampling, for example, high-rate sampling on the analog side in order to model the analog, and then, of course, run the digital communication system at its natural rates. I would like to acknowledge Bill Hughes from GE Corporate Research, who back in 1990 developed the concept for pacers and also methods for controlling buffer growth.